large company. We have a lot of contributors in forecasting, so no talk would really be complete without acknowledging the broad set of work that's been done there. So I thought I would start with a little bit of a overview or timeline of the history of forecasting at Google, and this is my attempt at putting this together. It's a little bit my personal perspective, and you'll see I'm going to call out a lot of my team's work in here, but really there are many teams that have contributed here, so you can see the list of teams down at the bottom there. Sorry, my pointer's not as cool as Pierre's, but hopefully you can still see it. As far as I know, the first forecasting tool, production system tool that was built at Google internally for forecasting was around 2010. That was the Fargo tool. It was for forecasting search growth at Google. It was a univariate forecasting model. It's still there. Back in that time period, we were also working on BSTS for folks that have seen that. So that was really some of the early work in the forecasting space or univariate forecasting models. I joined the company in 2017, and we've been doing a lot of work since then, and even before I joined, of course, around capacity planning. And so that's been a little bit of the focus of my talk in infrastructure capacity planning. It's what I'll kind of both focus on my work and what I'll talk about a little bit today. During that time period, we also did a lot of work in retail forecasting. So retail cloud customers being a big aspect or component of our cloud business. So there was a lot of research done in that area also. But what you'll see is some of these problem domains that we're working on really drove the research agenda and the research focus of the work that we were doing. So capacity planning, for example, we're really about trying to predict the value of upper quantiles of forecast distributions and using that to set capacity. So you're going to see that, for example, a lot of our, there it is. I'm getting it. Move over there. A lot of our focus here was around distributional accuracy, getting the forecast error distributions, the forecast distributions to really hit those upper quantiles properly. So that was a big focus of our work, starting as early as the 2015, 2020 time period. And additionally, speed. So we're running these forecasts for lots of nodes simultaneously, so speed and then hierarchical coherence, where we're trying to forecast and plan across multiple geographic dimensions or resource types or business unit dimensions simultaneously. So those were some of the three areas that we focused a lot on during that time period, was really getting those pieces together. And we continue to expand our tool set as a result of that, and did some upgrading on Fargo, for example. Whoops. And then most recently, 2021 to 2025 time period, we've kind of been extending the capacity planning framework really out to capacity management, meaning thinking a little bit more short horizon forecast, more granular forecast. How do we move resources and move capacity of resources more fluidly and optimize around that? A big focus on stockout awareness has been another area we've done a lot of work. And in general, what I've seen over the past few years is the complexity of our business and the complexity of the space has just grown dramatically. So that's going to be a big part of my talk, is just how has that complexity expansion really affected the work that we've done at Google. And of course, we've also been spending a lot of time just trying to benchmark our tools, making sure that the resources and tools that we're using at Google are really state-of-the-art tools and capabilities that we're bringing to bear to the problems. So I put this slide together kind of to highlight some of the complexity of the type of work that we're doing. So currently Google Cloud is in about 40 different regions. You can access Google Cloud, and that's over 120 plus cloud availability zones and hundreds of clusters backing that. When I joined the company, we were in about a dozen regions and a much smaller number of zones, and so that expansion has grown quite quickly. Additionally, we now offer over 40 different virtual machine families, which adds another layer of complexity to the problem space. 20 different major chip types that are kind of installed in our server base behind those different VM families that you can choose from. And then we're not just planning for compute capacity, we're actually planning across compute, storage, network, I/O, GPU and TPU resources, et cetera. So a lot of complexity across that area as well. And then we're doing this not just for Google Cloud, but for 10 or more different internal product areas, as well as thousands of external customers. So today we're generating about 1 million forecasts a day just for the capacity planning application area. So I know there's other businesses that are out there that number hasn't seen that big, but certainly it does present a set of challenges for us, especially the diversity of resource types and intersectionalities that are there. And we've been doing this in an environment of increasing uncertainty, so the market, the economy, the business growth, the AI kind of revolution's really driven a lot of change in the infrastructure and cloud marketplace. And so trying to plan under those changes, as well as the political environment, the tariff environment, et cetera, has actually created quite an interesting set of challenges for us. And then we're also doing this in a time of tightening supply, as demand has just been skyrocketing for a lot of compute services. And so the risk and value of planning at lead time really has increased. And so that's tightened our supply market. We have chips, components, power, et cetera, where we're all kind of, the value of missing that forecast or under forecasting is really, really critical. So to make it concrete, here's an example of our SKU lineup, kind of a timeline of our SKU lineup over the years. And when I came in to the company in 2017, we were really planning one SKU. So we were planning the N1 SKU, which is our general purpose computing platform is N1. So that was the one kind of virtual machine product that we had to forecast at the time. And now we're at about, like I said, about 40 different products, and you can see the evolution over time. That's driven a lot of the increasing complexity and challenges that we've been facing. Another area that's been interesting for us is as we've added more virtual machine products, there's actually a lot of fungibility opportunities that present themselves from having that product availability. So we don't, this is an example for E2, which is our kind of cost optimized virtual machine. So I can deliver an E2 virtual machine from at least 5 different hardware sources, right? So I actually have this fungibility between 3 different Intel platforms, a couple different AMD platforms, and then a few others actually as well. So that creates, it's good for efficiency, right? I can pull, I don't have to have one set of capacity just dedicated to E2. I can use alternate resources, but it's actually creates some complication for planning. And some of this fungibility is instantaneous and some of it isn't, meaning like if I want to purpose a different family to an E2 family, I might have to reboot, I might have to do something that's going to cause some delay, move it to a different pool, et cetera. So I may have some fungibility that's instantaneous, some that takes a few hours, some that takes a few days. And so that all has to go into the models that we use for how much capacity we plan by resource. So, and this is an example of what that actually looks like in practice. So a lot of content on the slide here, but if I get the pointer to work again, oops. So this is actually an example from one of our general purpose families again. But if I go back to the picture here, so I can sell you I keep hitting the wrong. I can sell you a general purpose VM actually in multiple machine types. So I can sell it to you as high memory, I can sell it to you as standard, or I can sell it to you as low memory. So this example is within a given family, what does that fungibility look like? And so the green, blue, and orange series at the bottom here are the different time series for the high memory, standard memory, and low memory. This is 6 days of data, I think, for one example. And you can see that they spike at different times, right? So I've actually got the orange one here that the spiking is completely offset from the other time period, and it's actually the high memory one, which is the most expensive one. So I have this dynamic interplay where if I were to plan each of these, if I were to have high memory hardware backing high memory SKUs and low memory hardware backing low memory SKUs, I'd have to plan capacity for each of these, which means I need kind of capacity up at this purple line, which is the sum of the three different lines added up together. So that would be my kind of sum of daily peaks, or peak of daily, one of those. So I would have to have capacity covering the three of those together. On the other hand, if I could serve it all with one hardware type, then I'd be way down at this brown line, which is actually more than 20% lower in terms of cost. So the challenge that's kind of interesting here is if I did it all with one hardware type, I'd have to use high memory hardware for all three of these machine types, which is more expensive. So I have this cost trade-off between efficiency between cost of hardware, or trade-off between value of the efficiency and the cost of the hardware backing it. And so that's another type of optimization that we're actually playing with as part of the planning work that we do. Second type of problem that brings challenges to us is actually needing to plan across multiple workloads, or planning across workloads that involve multiple resource types. So what I've shown here is, this is just simulated data, but pretty close to reality, where we'll have, you may bring a workload to Google Cloud as an external customer. We have one internally that requires compute, requires RAM memory. It may require GPU or TPU resources. It may have disk storage, it may have SSD storage. It's going to require a certain amount of power. And so if you think about it, I need to, in order for me to say I have capacity available to serve your workload, I need to have all of these capacities available, right? And so I have multiple resource types. The demands are correlated between, obviously if I need more compute, the chances of me needing more RAM is higher. But my risk of stock out is actually correlated between the different resource types. And so I think of this as kind of a multi-item news vendor problem, where we're trying to plan capacity across these types simultaneously. And like I said, one stocked out equals all stocked out is kind of the challenge that we have. And not all workloads are created equal. I could have one customer comes in that's a standard computing workload, doesn't use any GPU or TPU resources, doesn't use SSD. Then I could have a second customer that comes in that uses a ton of machine learning hardware, GPU or TPU, as well as a lot of SSD, a lot of network. And so very different variety across the different workload types that I'd have to deal with. And then obviously the cost of these resources is quite different as well. So network and disk are relatively cheap, for example, compared to some of the other stuff on the list. So given the increasing complexities that we've been having, I want to kind of talk a little bit more detail about how we've been upgrading our systems to kind of support that complexity. So I did a little bit of a walkthrough here of the kind of comparison here. So we've moved from doing essentially daily forecasts, where we take daily samples of data. So I might, for example, sample the peak value of each of the past days and use that as an input to my time series forecasting model, or an upper quantile of that history and use that as an input, and then forecast daily values going forward. And that gives me a little bit of that helps me plan to my peaks, right? But I'm actually missing a lot of detail in the daily workload shape. And you saw in the previous example, those workload shapes during the day can be highly volatile, even if the peak to average ratio is the same. They can vary quite differently. So now we move to a much more granular view, where we're looking at hourly data and actually even 5-minute data, using that to make much more clearer forecasts and understanding of the intraday distribution that is happening in our workloads. And then that enables us to plan. If I know I want to hit an SLO of some upper percentile, I know exactly how many values during the day are going to be at what quantile of the distribution that I'm forecasting. So that's been a big upgrade for us. Another big upgrade for us is moving essentially from models that spit out point forecasts, and then we backtest them to generate uncertainty ranges, to doing a lot more, a lot richer forecast distributional modeling directly. So we're forecasting all quantiles through the distribution and using correlated sample paths to help improve the quality of those forecasts when we have components that are related, for example. We've also done a lot of work in blending over time horizons. So we have this idea of a model that is tuned for multiple horizons, and we stitch it together. So back, I would say, when we first started working on capacity planning, we focused on one problem at a time and kind of said, all right, I know that it's going to take me 12 weeks, as an example, to get a server delivered to a data center, installed and up and running. So I'm going to tune my model to 12-week horizon and just plan to that, and that's going to be, my loss function is going to be targeted at how do I minimize the expectation loss at 12 weeks. And now we've been able to, so that has worked really well for that particular problem. But then I also would have another problem where I need to forecast at a longer horizon. Let's say I'm using those same forecasts to drive component purchases for long lead time components at 6 months or 9 months or something like that. So now I have the need for a forecast that's tuned at 9 months and a forecast that's tuned to 12 weeks. So we've invested a lot in kind of blending those together so that when I do make those multiple forecasts, they're actually fully consistent and coherent through the time. So that's been another area of investment for us. We've also done a lot of work on separating kind of organic demand from inorganic demand, which may be things like a new customer arrives, a customer launches a workload, a new workload, we launch a new workload or a new service internally, for example. And so those will all drive, those we would all consider those to be inorganic demand. And so we do some forecasting where we strip out inorganics and forecast just the organic demand. We do some forecasting where we bring it all together. And then we do a lot of work on modeling the distribution of inorganic demand as well. So that's been another area, a big area of focus for us. And then really moving, kind of upgrading our backtesting framework to be increasingly automated. I think I've overstated it in saying it was largely manual here. It's actually quite automated in the past, but we've continued to enhance that capability with the tool set that we have. And then really trying to do this all through a single, simple API so that everything is productionized and we're able to run these models kind of consistently. So big area of investment in the team around kind of just getting ahead of the complexity that we're seeing. So with that, I want to kind of switch gears a little bit and talk about some of the advancements that we've done with our neural net forecasting model. So StarryNet is our neural net forecasting model. For folks that it's been presented at ISF before, so folks have probably seen it, but essentially it's a structural neural net based model. So we built it around a framework that uses seasonality, trend, autoregressive residuals, so you can kind of get where the name comes from, a residual correction, power transformation, and then it's all bringing the power of the neural net on top of that. So this kind of hybrid approach has enabled us to have the power of a neural net, but still the explainability and kind of guidance that the structured model enables. So that's been a project in the team for a few years. The picture here, I think, helps to clarify it a little bit, but essentially it's built in different blocks for each of those components. So there's a trend block, a seasonality block, and a cleaning, for example, cleaning block. So I think this change point detection block is actually quite an interesting example. So here you see one of these this top one is the overall series, the history and the forecast. You can see one of these kind of inorganic events. So our change point detection model is going to find that inorganic event and adjust for it or remove it from the series so we capture the latent trend exogenous to that inorganic event and then continue to model from there. So then we take each of these steps, we run the step, run the block, pull out the residuals, and then use that for our next step. So it goes through the cleaning step, the change point detection step, the trend step, and then a seasonality model where in this case it was day of week was the one that was selected. And finally, we have the resulting residuals, and then you can see that residual correction item here where the model is trying to bring itself back to the long-term trend. So you'll see that as part of the model also. So this project's been going on for a few years. Like I said, the latest innovation we've been doing is actually looking at, it was interesting, Pierre's talk was about data and having a lot of data. You'd think we have a lot of data at Google, but actually compared to the amount of data that it takes to make one of these models really run well, we found the more data we can throw at, the better it's going to perform. So we started simulating data, and I'll call out a lot of folks on the team. I'll do acknowledgments at the end. But a lot of folks on the team contributed to that effort of bringing in more and more simulated data. So this is Pablo made this slide. It's got 12 series. Some of them are simulated, some of them are real, and essentially we're just simulating data through simulations of exponential smoothing and then feeding that and training the model. So that effort, we actually kind of spent a lot of time doing that, and Pablo actually helped us train a model with 2 trillion time points, which I don't know if this data is fully up to date, but it was more than at least we had ever seen at the time in terms of the amount of time points that were generated. And using the simple model that was, simple exponential smoothing kind of approach, it's pretty cheap to generate, so it ran in like 3 days on a V100. And that actually gave us quite a bit of performance improvement. So this was the results actually with a much smaller model. So this one's trained on about 1 million time series simulations. So, maybe that's a few 100 million time points. But even with training, so the model saw no M4 data before, trained it on 1 million time series that were all simulated, and actually pretty much tied the winner from the competition. And I had a good exchange with Pablo about if we ran this with more data or data that was simulated in a data generating process that was more aligned with the specific problem at hand, how much better could we do? And he thinks we can do even better than what's shown here. So really exciting research that we're now able to do with simulated data. And so that's been a big focus for the team going forward. Also, maybe if I can put my simulated data in Pierre's data market, I think we can make some money. So that's interesting. So kind of taking it back to the timeline and the framework, the takeaway for me from the work that we've done, and I think the one lesson I would kind of take back is by really focusing on the specific business problems and the specific complexities that we had that drove a lot of innovation in the team. And so things like the capacity planning work, driving focus on distributional accuracy, speed, coherence, and then the recent efforts driving more and more investment in kind of aligning, and I didn't talk too much about it, but this piece about minimizing stockouts and being stockout aware really drove a lot of investment in what I call SLO or service level driven capacity models, where we're really trying to target a specific SLO. Explainability, again, you saw that with the StarryNet model and the segmentation and breakdown that it has. Cross-resource accuracy, and then this idea of pre-training to further improve accuracy. So I did want to highlight one kind of really interesting just piece of work coming from across the organization. So this is not my team's work, but this came out about June. It's the Google Weather Lab and work that they had done forecasting cyclone paths. And so I just watched, it's about a 20-second video, but it just really blows my mind to see the type of modeling that's being done and the type of work that's being done. So this is coming out of the DeepMind team, forecasting specifically cyclone paths. I'm not a weather guy, but it looks pretty cool to me. See if I can go one more here. Okay, so that's That's the end of my talk. I did want to plug the other research talks, the other talks from Google that are happening actually right after this session. So meeting room 7, I believe at 11:10, there's 4 talks from Casey, Pablo, Weijian, Li Juan. So welcome folks to go see those as well, and you'll get a lot of more detail. And those folks have been involved in a lot of work I described here. So big acknowledgement and thank you to them and the other folks at Google that contributed to this. And that's how to get in touch with me.
So, Chris, very interesting. So I have actually a couple of questions. When you one slide you showed Google does per day about 1 million forecasts. Then the latest structure you have change daily forecast to hourly forecast. That means the number of forecast models can be multiple millions. How come you can do this, or how many models you will be used, like different types, or just like auto-regressive, or just one count and forecast everything?
A good question. Thank you, Jungjun. Nice to appreciate you coming to the talk. So what we do is we generate 1 million approximately forecast outputs per day, right? And so moving from daily denominated forecast to hourly or 5-minutely denominated forecast, we're still generating, I still consider that 1, right? And actually behind the scenes, we're running multiple models here. So I might generate the same forecast 20 times, I also only called that 1. So I think what you were asking was along those lines. Yeah.
So many, it's kind of amazing. How can we run like 1 million forecasts per day and maybe more if we do the hourly forecasts? Yeah. Maybe let me check a second. You have this one slide showed one stocked out equals all stocked out. Like from my imagination, Google is so like a gigantic company. How can we do this? One stocked out equals all stocked out. Yeah.
Yeah. So what I meant there was one resource not available, then I can't deliver the workload. So if you come to me, for example, and you say, hey, I want to bring a workload to Google Cloud, and you start to run it, and you start using a ton of disk, and we run out of disk in the location for the type of service that you're running, right? It won't bring down Google, but you'll no longer be able to get disk, right? And so then that workload is going to, if your workload requires it in order to move forward, it's going to stop, right? So this is a really bad thing. We want to kind of always avoid it. Yes. So that's why we're having to plan capacity on all these pieces so that the chance of that happening is extremely low, right? So I mainly brought that up is to illustrate the challenge of the problem is I don't want that scenario to happen, not that it happens all the time.
Can I ask one more? Okay, so like when you showed this starry net, one power transformation is called Eo Johnson because Rich Johnson, he was my colleague, yeah.
Okay.
And I think Eo, he got his PhD from Wisconsin and he went back to South Korea. So what kind of framework you apply this Eo Johnson transformation? I mean, like before this one was called the Box-Cox transformation. So why you choose this Eo, I mean, like your model choose Eo Johnson transformation?
Yeah, good question. So we did use Box-Cox for quite a while, and if you talk with Casey afterward, he can probably explain why he kept insisting we switch it to the Eo Johnson. Oh. But that's the whole idea is we're just doing some power transformation to linearize the history.
It's great, yeah. Maybe I should stop.
Thank you, Jungjun.
Right. If that's right, I can ask a question?
Sure.
Thank you very much for your talk. Very, very interesting. So my question is about sustainability. And you mentioned about the speed of calculations, but does Google consider at all in the equation, apart from forecast accuracy or forecast performance, sustainability aspects of producing forecasts and how we can improve that?
Thank you so much for asking about that, Fotios. So we have done a ton of work actually in making the way we run workloads at Google green. And so, for example, as you can see, these workloads are going to have diurnal cycles. They're going to vary by location. So we actually have a model running behind the scenes that will take any workload that's not location specific and actually move it around globally to find the greenest or lowest cost location that workload can run. So we take about 40 or 50% of our batch workloads are able to move globally. And so we'll do that, kind of greenhouse gas based, excuse me, movement where we take advantage of where the power utilization is most green and move the workloads there. So that's how I would say that's happening. It can't happen for every workload. We have some, for example, if I have some workload that needs to run a specific location or a forecast that's tied to a specific planning for a specific node that has to run there, then I'm stuck there. But in general, we're trying to improve this.
All right. Oh, please.
Thank you. You mentioned the increasing uncertainty, and I'm wondering if you have a scientific, analytical approach to deal with scenarios, to evaluate different scenarios that are dealing with the increasing uncertainty.
Yeah, this has been a big focus for us. I didn't bring it out specifically in the talk, but it's been definitely another area, especially as we get into longer horizon forecasting. So short horizons, we pretty much, we're extrapolating the trend, right, is essentially what's going on. And then as we get further out in time, we have to think more from a scenario basis. And so we actually have one of our power forecasting researchers here, Li Juan, who is going to be also giving a talk in the next section. And I encourage you to chat with her. She actually does forecasts out, I think, to 5 or 10 years. And so it's much more of a scenario-based approach that we're bringing into the fray there. But I would say there's plenty more work to do in that area, especially as we model out the different economic situations. So that's been a big focus. And we've also, by the way, started a lot of work on kind of sentiment-based forecasting. So looking at, what's going to happen with the AI market over the, next few years, and what is sentiment saying about that, and trying to use that to enhance the quality of our models. So that's another area I'm excited about, kind of bringing more of that information into the forecasts.
Hi, thank you for the very interesting talk. For me, it was very interesting to see that data scale helps a lot, especially with StarryNet, where you're trained with ETS simulations and then it helped performance. So my question to you is, do you think model scale also helps a lot? Because a lot of academic research focuses these days on increasing the size of models to billions of parameters, etc. And my second question is, do you think different model architectures are also useful to explore? Because I guess from your slide, StarryNet is a very simple architecture. It has a neural net, and then it's just trained on a lot of data, which gives it the performance. So do you think model scale and new model architectures are useful to explore? Thank you.
Yeah, so I do. I think there's also something related to the ratio of the amount of data to the size of the model, right? And so if I have a model that's super complicated, it just means I need a ton more data to make it work, right? And so that was, I think, part of the focus of what drove us even to StarryNet in the first place was, we know we don't have that much data. We want to guide the model into the right direction of, it's going to have trend. It's going to have seasonality. Why does it have to invent that, kind of a priori rather than building that structure into the model? So we give up some degrees of freedom when we do that, right? And so it simplifies the training. We're training on the residuals of a structured model that may or may not be the perfect fit, right? Especially when you think about the seasonality, for example. But that there was a definite trade-off that we're making there around giving it the head start from the structure and then being able to leverage the data. So we continue to play with that trade-off in our work.
Thank you, Chris. Very interesting talk. So my question is also about StarryNet. From the perspective of Google, from what kind of motivations you guys want to develop a kind of a modified neural network instead of using other neural networks, and that may also correlate to how stereonet may differ from other neural network models thinking.
Yeah, so, we really were, if there was something else available when we started that would have addressed the problem as well as we thought we could with StarryNet, we would have been happy to use that, right? And I still feel that way. So it's not necessarily, okay, we have to home grow everything, right? But by owning the kind of structure and the design of the model, we could really tailor it to the problems we were trying to solve and continue to build upon that as new problems came into the fray. So that's worked quite well for us. It's given us the ability to kind of design both the current product as well as the roadmap based on what we know our needs are going to be. And so that's been the impetus there, to just kind of tailor it to our specific problems at hand.
Thank you.
Chris, back to me if that's all right. I understand you had the right part of your timeline a bit, vague, and I would assume this has to do also with restrictions with what you can share with us and what you cannot.
I can't hear you quite clearly, Photios. Just get it close. Yeah.
So you had the right part of your timeline a bit, vague, 2026 onwards when it comes to Google and projects. And I would assume that is because you cannot share very much with us. But from a personal perspective, what are the big challenges in forecasting in the next, let's say, 5-10 years as you see it?
Yeah, I did keep it vague, and partly it's not clear to me what's going to hit next, right? I think that some of the movements in the market have been surprises to everybody, and so, but I think with the AI the role of AI and the demand that generates for computing is definitely a key area where we're seeing the need to have a lot of focus, and so. The question about scenarios and modeling scenarios and growth scenarios for that, and it's definitely one of the key areas that we're thinking about in terms of getting ahead to the future. Yeah, we'll see what else happens. A lot of great work in foundational models, happening now. So, I think there's the future, the outlook for the future is very bright, and we're just trying to get as well positioned for that as we can.
Any other questions at all? Anybody else?
It's really exciting talk. I wonder, so you talk a little bit about uncertainty and quantification. Can you talk a little bit about the techniques that developed or you're using by Google, and also how we will actually utilizing the estimation of the uncertainty for the practical applications?
The uncertainty estimation specifically?
Yeah.
Yeah, so Casey and I actually gave a talk in 2020 at ISF about the backtesting framework that we use and how we use that to generate error distributions that reflect out of sample error at a specific horizon. So I would say that's a good reference. The video is still available online. It talks a little bit about that aspect of uncertainty estimation. As we've now moved from kind of the daily to the hourly models and are thinking more deeply about these fungibility problems, we're starting to make some enhancements to that. But I would say that general concept of looking at out of sample errors and using that to guide our understanding of uncertainty has certainly been, especially at the shorter horizons, a key tenet of how we're doing uncertainty modeling. Does that answer your question?
Yeah, definitely. Thank you.
Sure.
Let's thank again Chris Fry for this beautiful talk.
Thank you.
And I think next up is a coffee break. So I'm not sure where this is happening, but thank you so much all.